welcome back for the next session. In the previous one, we discussed about the basics of electrostats. By the way, when I say basic, it doesn't mean all the basics are covered. There is a lot remaining, and in this session, I will cover that remaining part. Still, it's not over. Today, we will discuss about electric field altogether. Also, one more thing, a lot of you must be wondering about what about the numericals of quantization of charge, Coulomb's law, induction, and your superposition principle. So don't worry, I will have another session with you people only for the numericals or NCERT questions. So we will do that, okay, that you can keep on the back burner right now. And let us focus on the thing called as electric field. Now, what is electric field? So, electric field due to a given charge, let us suppose I have a charge, okay. So, the electric field for that charge is the space around that charge in which its force can be experienced by a unit positive charge or any other charge. Okay, unit positive charge or any other charge. Let me go with the definition. Electric field due to a given charge is the space around the charge in which electrostatic force of attraction or repulsion due to the charge can be experienced by any other charge. By the way, it is not necessary that the definition which I have written and which I am telling you match exactly. It's just the words which are reframed. Otherwise, the meaning is same. For example, if I am the charge and someone, you as my student is another charge. So when you are coming to me, there is a space around me in which you will experience my force. My force can be attractive, that is we will have a good vibe between us, or my force can be repulsive, that means we don't have that vibe between us. So that is my electric field. Now, there are two kinds of charge, the source charge, that is myself, who produces the electric field, and the test charge, that is you, who experiences my field, or who is the test, who is helping to test things. Okay, that's why it is called as test charge. Now, electric field intensity. Electric field intensity is nothing but electric field only. But here we are specifying a few things. So what we are saying, it is the strength of electric field at a point. For example, as I said, if I am the source charge, I have an electric field. Now that electric field is not same everywhere. It is different. So if I want to find out my strength, I need a test charge. So it is defined as the force experienced by a unit positive charge placed at that point. So let us consider a unit positive charge. That charge comes in my field at, let us suppose, this point. So what is the force experienced by it? That is called as electric field intensity, represented by E. Vector sign is there, that means it's a vector quantity. The formula is E is equals to F by Q naught, where Q naught is the test charge. Okay, now what about the unit? Force, it is Newton. Charge, it is Coulomb. So Newton per Coulomb. And a lot of time they have asked this in boards. Name the physical quantity or write the physical quantity whose unit is Newton per Coulomb. So the answer is electric field, and remember it's a vector quantity. Now see, for a positive charge the electric field is outwards, for a negative charge it is inwards. Okay, again it is the pure mathematical definition for electric field. Now the test charge will have its own electric field, okay. And the test charge, when it is coming in the source charge electric field, it can modify because it has its own electric field. Okay, so in order to minimize that effect, we write electric field is equal to limit Q naught tends to 0 F by Q naught. Okay, now electric field intensity due to a point charge. So what we have considered? We have considered Q, capital Q, which is the source charge. Okay. I want to find out the electric field intensity of capital Q at a point P. So what I have done? I have taken a test charge. So do you remember Coulomb's law? What was it saying? F is equal to K, where K means 1 by 4 pi epsilon naught Q1 Q2 by R square. Now this is my distance. So what can I write? F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay. Where this R naught cap is a unit vector. What is it updating you? The direction. Or you can write along QP. If you don't want to write the unit vector, no problem. Write along QP. Okay. Now what was the definition for electric field intensity? F by Q naught. So if I put the values, what am I getting? I am getting the formula for electric field, which is E is equals to 1 by 4 pi epsilon naught Q by R square, where Q means the source charge, not the test charge. Now, one thing, from the center, that is from the charge, if I have a test source charge, it will make a spherical symmetry. It will be a sphere. The radius is same at every point. So, it provides you the electric field due to a single charge is spherically symmetric. Okay. After this, what we will study is the vector form. That's the same thing which we have all. Okay. I told you I will tell you about electric field lines, but before that, there is this question. What is the importance of this electric field or the significance of electric field? So, if I know the electric field, if I know the charge, I can find out the force. So, F is equal to Q naught E. Now, let us come to this thing called as electric field lines. Now, what are electric field lines? Electric field lines is a path, okay, straight or curved in the electric field such that the tangent to it at any point gives the direction of electric field intensity at that point. So it can be a straight line, it can be a curve, but at every point when you will want to find out the direction of electric field intensity or electric field, you have to just draw a tangent. So this is the electric field lines. This is for positive and negative charge. We call this as a dipole. I will teach you later what do you mean by dipole also. Okay. Now what are the properties? First one, they form continuous curves. That is, they are continuous curves. What do you mean by continuous curves? It means that they move from positive to negative. Do you remember I told you that the electric field for positive charge is always outward, for a negative it is always inwards. So if I have a positive and negative, it moves from positive to negative. Okay, but it is not continuous closed loop. Do you remember magnetic field lines you studied in grade 10? We said that outside the magnet it is north to south, inside it is south to north. That was continuous closed loop. Here, electric field lines, whether it is outside, whether it is inside, it is always from positive to negative. Second, the tangent to the electric field line gives the direction of electric field, which we have already said in the definition. Now, no two electric field lines intersect each other, because if they do so, then at the point of intersection there will be two directions, which is not possible. Okay, they are always normal to the surface of conductor. They contract longitudinally on account of attraction between unlike charges. So it's a very simple thing. You need not to go into the details for this. Now, the magnitude of field lines or field is represented by the density of field line. That means if more field lines are at a place, that means electric field is more. If less number of field lines are there, that means electric field is less. This one is in NCERT, a very interesting question. It says that show that the electric field intensity is more near the charge. So for that we have taken the concept of angle. I hope you remember in grade 11 you studied about angle. If you don't, the formula for angle is arc by radius. By the way, that is for plane angle. For solid angle, it is area by distance square. So what we are saying, that if I have a plus q charge at the apex of a cone, the number of radial field lines in a solid angle are same. That means here they should be same. What we have considered 2 points P1 and P2. I hope it is clear in your diagram. If you see it, if you are not able to, just zoom this a bit, you will see that. Okay, so what we can see, that I have taken 2 points P1 and P2, which are at distances R1 and R2 from plus q charge. Now, as I told you this formula, delta omega is equal to delta S by R square. So if I want to find out what is the area subtended by delta omega at P1, so I want to find, by the way, delta S1. That will be R1 square delta omega. If I want to find at P2, it will be R2 square delta omega. By the way, what we said, the number of field lines cutting the area element are same. Let me call this as N. Okay, that means electric field intensity is same. Now what is electric field intensity here? That is N upon, in first case it is R1 square delta omega, in second case it is E2 is equal to N upon R2 square delta omega. If I divide them, what am I getting? E1 by E2 is equal to R2 square by R1 square, that is E is inversely proportional to R square. Now let us come to this thing, a very important thing for you people, electric dipole. Very important thing, children. What do you mean by electric dipole? So it consists of a pair of equal and opposite point charges separated by a finite distance or a small distance. So I have a positive plus q charge here, negative minus q charge here. By the way, they should have the same magnitude. So if this is plus q, this is minus q. If this is plus 2q, this is minus 2q. Okay, and they're separated by a small finite distance. And what we are saying, that the distance we call as 2a. Okay, so that means from center it is a each on both sides. Okay, now this I will teach you later. Where is this important? Why this concept? Dipole moment is represented by P. Do you remember P, the symbol? We have used this for momentum. It's the same thing, but it's okay. So here it is dipole moment. What is dipole moment? It is the strength of electric dipole, and it is equal to the product of magnitude of either charge and distance between them. So P is equals to Q into 2A. That is the formula. By the way, this is very important. What is the direction of P? It is from minus Q to plus Q. That is negative to positive. Let's come to the unit. You will tell me the unit, by the way. What is the formula? P is equal to Q into 2A. So what should be the unit? It should be coulomb 2 meter or coulomb meter. We don't use 2 or 3. The unit is coulomb meter. Okay, and this is again a vector quantity. Now a very important thing for you people, ideal dipole. What do you mean by an ideal dipole? Ideal dipole means a dipole which is smallest, that is having no size. How can I get that? If the charge is very large and the distance is very small. So I will get an ideal dipole or a point dipole. Now the question arises, what is the significance of this electric dipole? It tells me about polar and non-polar dielectrics. Now you must be wondering, what is this polar and non-polar dielectric? I will teach you right now also, and this reference we will use in capacitors. So please understand this very sincerely. It's a very important topic for you people. So when I talk about non-polar dielectric, I told you na dipole means for positive and negative charges of same magnitude and separated by a finite distance. So if it is a non-polar, in that the center of the positive and the center of the negative, they coincide. Okay? In a non-polar, the center of the positive charge and the center of the negative charge, okay, center of mass of the positive charge coincides with the center of mass of the negative charge, the molecule behaves as non-polar. Okay? And if it is not coinciding, it's a polar molecule. Okay? Now dipole field, just like electric field, we say that an charged particle is having a field. Okay? So that is called as electric field. So a dipole is having a field, that is called as the dipole field. Okay? Now I want to find out the electric field intensity of an electric dipole at two places. Let us suppose, let me give you an example. Let us take this part itself. This can serve as an example. So if this is my dipole, one charge here, one charge here, I can find out the electric field intensity at two places. I want to find out this place. Also I want to find out at this place. By the way, they won't have the same electric field intensity. So you need to be careful with that part. Okay? So first of all, this is called as axial. This is called as equatorial. Okay? So first, let's find out the electric field intensity on an axial line. So what I have taken? I have a dipole AB, okay, minus Q charge is at A, plus Q charge is at B, and the distance we discussed that it has to be 2A, and I want to find out on the axial line. So at P point, I have a unit positive charge, and I want to find out the electric field intensity. Do you remember the formula? What was the formula? It was 1 by 4 pi epsilon naught Q by R square. This was the formula. Let me apply it. So for this charge, what will be the electric field intensity? This and this we are considering. So it will be E1 is equals to E1. By the way, this is what I mean. 1 by 4 pi epsilon naught Q, which is this charge. I have taken the magnitude. I have taken the magnitude. You can, if you don't want, you can just take minus also. There is no problem in that. So E1 is equal to 1 by 4 pi epsilon naught Q over AP square, which is, by the way, this distance from O to P is R and this is A. So what is the total? R plus A whole square. And what is the direction? Along PA. Why? Because this is negative, that is positive, so it will be it will get attracted towards this. Done? I want to find out the electric field intensity for B also, that is plus Q, that I am naming as E2. So E2 will be 1 by 4 pi epsilon naught Q by BP square, and that will be equal to, again let's think this is R, this is A. So what about this? It has to be R minus A whole square, and positive repel each other, so it will be towards BP. Okay, now I want to find out the total. Now one is moving toward this direction, one is moving toward this. So if I am taking this as positive, definitely this is negative. So if total E will be equal to E2 minus E1. I put the values. 1 by 4 pi epsilon naught and Q are common, taken out. Inside the bracket it is 1 upon R minus A whole square minus of 1 upon r plus a whole square. Okay, so the LCM is taken, r square minus a square whole square. Numerator we have r plus a whole square minus r minus a whole square. If I solve this, what am I getting? Q by 4 pi epsilon naught 4ar upon r square minus a square whole square. Now this 4ar I want to write it separately. So can I write q into 2a into 2r upon 4 pi epsilon naught r square minus a square whole square? That's the same thing. But do you remember q into 2a? That's called as p. So p into 2r over 4 pi epsilon naught r square minus a square whole square. If the dipole is short, and I say short means 2a is very less than r. So that means I can neglect a. So what am I getting? It is E is equal to 2p over 4 pi epsilon naught r cube. Okay, remember this formula. This is a very important formula. Now if you remember, I was sharing with you that in the first case I took on the axial line. Now I want to find out on the equatorial line. Again, this is a very important derivation for you people. So again, what have I done? I have taken a dipole, minus q plus q. O is the center, 2a is the distance. That means this distance is a, this distance is a. And what have I taken? This point P is again the point at which I want to find out the electric field intensity. Okay. What about this OP? This OP I am taking as R. I hope nobody has a problem with that. So, what about the electric field intensity? Here there is a plus 1 coulomb charge. So electric field intensity, it will be equal to E1 is equals to 1 by 4 pi epsilon naught Q over AP square, and AP is R square plus A square. I hope everyone remembers Pythagoras theorem. This is A, this is R, this is hypotenuse of a right angle triangle. So R, this square is equal to this square plus this square. That's why we have taken this. By the way, the direction, it is along PA. It is important for you to write the direction here. I haven't written. I'm sorry for that, but you should write. Now, this angle we are considering as theta. If this is the angle theta, two parallel lines transversal, I think there is something called as alternate interior angles. So if this is the angle theta, this will be theta. That means, do you remember vectors? Resolution of a vector. So this is the vector. It can be resolved into two components, this and this. This component, if you remember in 11th, we have told you that theta, wherever theta is taken, that is cos, the perpendicular one is sine. So this will be equal to E1 cos theta, this will be E1 sine theta. Done. We will come to this later. Now I want to find out electric field intensity at P due to plus Q charge. What will I get? It will be 1 by 4 pi epsilon naught Q by BP square. BP square, isn't it A square plus R square the same thing? So the magnitude is same. Again, the direction part, positive, repel. So this is going again, it can be resolved into two components. It will be E2 cos theta, E2 sin theta. Now, can you see a thing that this and this, E1 sin theta and E2 sin theta, they are acting at the same point, and they have the same magnitude also, but in opposite direction, so they cancel out, and these two, they get added up. So the total electric field will be equal to E1 cos theta plus E2 cos theta. Let us check that. I think that's the same thing. Yeah, Eureka. E1 cos theta plus E2 cos theta, and we discussed E1 and E2 have the same magnitude, so it will be E1 cos theta plus E1 cos theta. So that is 2 E1 cos theta. Done. Let's put the value of E1. So 2 into 1 by 4 pi epsilon naught q by r square plus a square cos theta. Okay, let's put the value of cos theta. Let's see the triangle again. Cos theta in this triangle. What about cos theta? Cos theta will be AO upon OP. And what is AO? A. And what about AP? AP will be under root of a square plus r square. I hope that's the same value. Oh, that's great. A upon r square plus a square to the power of half. So E is equals to, by the way, do you think this? Q into 2a is P. So P over 4 pi epsilon naught r square plus a square to the power of 3 by 2. In vector, put the direction also. Okay. As we discussed, if the dipole is short, 2a is very small as compared to r, neglected. What am I getting? E is equal to P by 4 pi epsilon naught r cube. Okay. What was axial? In axial it was more. So if I divide the two, what am I getting? It is E axial by E equatorial is equals to 2. It's an important derivation for you. You should be doing this. Okay. Now we will come to the next topic, which is electric field intensity at any point on the axis of a uniformly charged ring. Okay. By the way, I don't want to do it. Let's do it. Okay. So what have I done? I have taken a circular loop of radius of wire of negligible thickness, area, radius A, center O, perpendicular, everything you can read. It's nothing. So I have taken a part AB with the center C, and I want to find out the electric field intensity at this point. If this is positive plus Q charge, this is positive, they repel. So DE, okay. DE is 1 by 4 pi epsilon naught dq by Cp square. Okay. Cp square is again, this is Cp square they are talking about. So this is A, this is R, so obviously this is A square plus R square, and here we have taken the charges dq. Here the charge is dq. If the total charge is q, the circumference is 2 pi a, for this part it has to be q over 2 pi a. I hope you keep that in mind. So let us come to the derivation. Okay, again dE can be resolved into two components. Again we have found for the upper part. If you find for the diametrically opposite, what will happen? The things will cancel out, that is the sine theta ones, the cos theta one will remain. So the total will be summation of dE cos theta. Here we will put the value of dE, which we have already done, and cos theta. Children, please understand one thing. When you are deriving a thing, you should be having a diagram in front of you. That helps you a lot. Okay. Now we put the values of cos theta also. Okay. Now dl, the summation of dl will be 2 pi a. If I put all the values, this is what I get. E is equal to qr over 4 pi epsilon naught r square plus a square to the power of 3 by 2. If P point lies at the center, R is 0, E is 0. If R is very large as compared to A, then E is equals to QR over 4 pi epsilon naught R cube, that is Q over 4 pi epsilon naught. Isn't this the electric field intensity? We all know. Last two small topics we need to do, and then we will wind up this session for you people. Now this is a very important thing, electric dipole in a uniform electric field. So you can see this is the uniform electric field and this is the dipole. Now electric field is from positive to negative. This is negative. Obviously this will move towards the positive. This is positive. This will move towards the negative. Do you remember the formula for force using electric field? F is equals to QE. So here it will be minus of QE. Here it will be plus of QE. Another thing which you need to understand is that it is occurring like this, here and here. It's not on the same line of action. If this was happening here and here, I would say 0. But here it is here. This part is here. Can you see what is happening? It is rotating. And if a thing rotates, what comes into play? Torque. So, and by the way, what is the formula for torque? Tau is equals to force into perpendicular distance. Okay. Force into arm of couple, that is perpendicular distance. That is force into AC. Let's see AC. This is AC. This is theta. Let us find out. AC. This part I know. This is 2A. I know the hypotenuse. I want to find out the perpendicular. I have the angle. What should I use? Sin theta. So, your AC will be equal to AB sin theta. And what is AB? 2A. So, what am I getting? Force is QE into 2A sin theta. Q into 2A is P. So, tau is equal to PE sin theta or P cross E. Now comes the important part. Again, the direction is perpendicular to both. If the if the dipole moment is along electric field, theta is 0. In that scenario, torque is 0. This is stable equilibrium. Now, if it is opposite to E, theta is 180, what will happen? It will rotate. Okay, unstable equilibrium. And if it is perpendicular, in that scenario, tau is equal to PE, the maximum value. Now let us come to the last topic for this session. This is potential energy of dipole in uniform electric field. Okay, so I have a dipole at an angle theta in a uniform external electric field, which we already did, and we found the formula also. What was the formula? Tau is equals to PE sin theta. Okay, now this is at some angle. I want to rotate it further. That means I have to do some extra work. I want to rotate it by a small angle d theta. So what is the formula? dw is equals to tau d theta. Let's put the value of tau, which is PE sin theta. So dw is equal to PE sin theta d theta. I want to find out the total work done in rotating it from theta 1 to theta 2. So what should I do? I should integrate. This is what I am doing. So the total work done is integration from theta 1 to theta 2 PE sin theta. PE comes out. The integration of sin theta is minus of cos theta. The limit remains theta 1 to theta 2. I will put I take the minus sign outward. So U, that is energy. I hope everyone knows work done is potential energy. So the potential energy is minus of PE cos theta 2 minus cos theta 1. Now if the dipole was initially along the electric field, that means theta 1 is 0 and theta 2 is theta, because I want to orient it in that direction. If I put the values, what am I getting? U is equals to minus of PE in bracket cos theta minus 1. Let's take the other case. The dipole is perpendicular. In that scenario, theta 1 is 90, theta 2 is theta. So what am I getting? U is equals to minus of PE cos theta or minus P dot E. Again, do you remember? Energy. It is a scalar quantity. Okay. So it has to be a dot product. Okay. So this session was the concept of electric field, the electric field intensity due to a dipole. We discussed about dipole moment, or the electric field intensity on axial line, on equatorial, on a circular ring or loop. Okay, then the concept of torque for a dipole and potential energy. Okay. So next session will be about Gauss law, Gauss theorem, and electric field intensity related with Gauss theorem. So do come for that. Thank you so much.